iConnect Training is one of the leading providers of HVAC and electrical training units for the educational market worldwide. It is a brand of North Park Innovations Group Incorporated that specializes in designing and manufacturing high-tech products for the HVACR industry. So, what does it look like to manufacture a brand new technical training unit? All right, let's start this journey and place our order. Once an order has been placed, if any customization needs to be made to that particular product, we can actually go into the drafting and make customization like we're doing for this particular one, which is going to be the new counter and presentation for the new mobile studio. Once an order has been verified, the system automatically starts ordering the parts and components that goes to that particular build, and all of the construction begins. All the components are cut to specifications, and the construction of the handmade trainer begins. Let's go out and take a look. We're going to pass through a couple departments on our way, and we're going to watch this thing develop. Once the order has been verified, all of the components are hand-built. All of the framing is measured and cut to specifications from those CAD-style drawings that we've seen earlier. And then we'll go on to the drilling, fabricating process, where the entire frame and assembly has been built off from common stock items, all being done by hand. iConnect trainers are not built to be mass-produced. They are built to teach clearly. Hand building allows every component to be positioned for visibility, easy to trace and explain, and laid out in a way that makes sense to students. It's not just a system, it's a learning experience you can see. On an assembly line, speed matters. At iConnect, understanding matters more. Cutting of all the graphics is a multi-step process. We start with our 3-layer common stock, which is a black, white, black laminated stocking. We're going to use a CNC cutter to be able to do all the trimming. And then on this particular one, it's actually going to come back through and do a recut of the back to be able to open up the pocket, the access for this particular panel. Once our part has been placed back into the CNC machine, you would think things would move around. This table actually has vacuum controls. It's going to draw the plate down, keep it in position while our machine is doing the work. So we're going to apply a vacuum. We're going to draw the plate down. And that's actually going to be stationary for the machine to do its next process. To create a more hands-on experience, the entire piece of equipment from the factory is disassembled, repositioned so that the student and the instructor has complete access to all of the mechanicals. Everything is hand brazed into position and located for maximum convenience for instructional and serviceability of the piece of equipment. When creating an extended training experience like this from a factory piece of equipment, every piece of wiring will be required to be extended, color-coded, and matched so that it maintains its consistency with the manufacturer's specifications, the wiring diagrams, and eases in the diagnostics so that we're following the original wiring pattern, and we are now extending all these components to every one of the individual items. After assembly, every product is thoroughly tested. All of the accompanying curriculum and books are provided for the particular trainer. Everything is hand packaged and delivered to your door. So if you'd like to learn more about iConnect, we encourage you to reach out to them directly at iconnecttraining.com. And thank you for joining us on this ESCO Roadshow. Well, hello everyone. Thank you so much for joining us once again. Scott, hey, glad that you're hanging out with us today. We're going to dive into a really intriguing conversation. It's one that gets a lot of controversy in the industry, and I've got a really funny example that I'm going to have to share with you here in just a minute. It's going to be a really good one. Everyone, let us know where you're joining from. And along the way, we're going to be asking some questions of you. We're going to want your involvement in this conversation because it will help direct the way that we go through some of this instruction. Todd, thanks for joining us from Barbados, man, out on his honeymoon. Tom, he's got it rough, right? He
Yeah,
takes
he's got it rough.
yeah. He's living in California, so he takes his vacations in Barbados. Man,
Yeah,
Kendrick,
and
you and I know what it's
dedicated,
like here in the Midwest, right?
yeah, and dedicated on his honeymoon.
That's right. And Todd, we really appreciate you hanging out. This is going to be a good conversation. Joining us today is my friend Tom Cates from Lennox. How are you, sir?
Good. I'm good.
All right. So this is a really intriguing conversation to get into because there's a lot of questions. Hey, the office is joining us. We got a whole bunch of them up in the office right now. Oh, that's right. I'm sorry. Did I say honeymoon 10-year anniversary? I'm so sorry. Professor Silverstein joining us up there. Paul Leonardi joining us from the Jersey Shore. Sunny too. I bet it is pretty nice out there right now. All right, so we're going to spend some time today, Tom, talking about the difference between ERVs and HRVs. And when we start looking at high performance homes, there are times where they are absolutely required. So I've got a really interesting story to share. It's one of my favorite ones when I talk about high efficiency homes. And most people get a kick out of this one. All right, so this is like 15 years ago, okay? And a good friend of mine, one of my customers, because this is before I got really dedicated into the commercial refrigeration world. I was a technician. I was doing a mix of commercial refrigeration and residential HVAC, some custom design. Hey, Osvaldo, join us from Belize. We got a bunch of tropical viewers today. This is going to be an interesting conversation, especially with y'all that are dealing with humidity down there, like in Belize. So one of my customers, he's a farmer. He's getting ready to build a new house. He's an engineer, and he wants to be the general manager, Tom. So he says, "Okay, I'm gonna design. I'm gonna be a general manager. I'm gonna build this house, and if I have any problems along the way, can I still reach out to you, even though you're not going to be the contractor?" I'm like, "Yeah, that's no problem." Because he was going to do a geothermal system, which we weren't, installing geothermals. So he designs this home. This is back when we're really starting to talk about, high efficiency homes. So two-story farmhouse. It's probably 3,000 square feet or so above ground. It has one of the insulated foam core foundations. So it's like a 10 or 12-inch poured concrete insulated, form foundation. It's a geothermal heat pump with a loop out in a pond in the backyard. He encapsulates the entire structure. So 6-inch walls, right? Spray foams all of the walls, but also spray foams the attic up to the decking. All of the exterior walls have vapor barrier. It's just a very heavily insulated home. Hey, Les joining us from Arizona. Hey, what's your weather out there? Are you on the dry side right now? This would be a good one for you. All right. So, so he gives me a call. All right. So he builds the house. It's in into summer, gets it all put together. Calls me in the fall. He says, "All right, Cliff, I got a problem." I said, "What's that?" He says, "Promise to take me serious." I'm like, "I'll try." "Well, what do you got?" He says, "Okay, I can't fart in my own house." And I said, how am I supposed to take that serious? He says, "Well, like the first time that I farted in the stairs and someone walked through it an hour later, it was super funny. But that didn't last very long. Then it wasn't funny at all." Man, Adam joining us too. This is great. Glad you guys are hanging out with us today. Our FM hero buddies are bringing the team. And I said, "Well, that is quite interesting." He says, "It's not only that." He says, "It's like fall and I've got moisture dripping off from the windows. My wife cooks a meal and you can smell it the next morning." He says, "And remember how I put that wood fireplace in for emergency heat?" He says, "Power went out, fired up the wood burner, the thing choked out about 2 hours later. What do I do?" I'm like, "You gotta get some fresh air into this house." He says, "But the whole point is not to."
Yeah, it's crazy, isn't it? We build these high performance homes, and then we have to go and cut a whole bunch of holes in them to make them so they can breathe again.
When I told him that, I thought he was going to lose it. He's like, what do you mean? I built this thing for efficiency. And now you're telling me, yeah, exactly. I got to cut 8-inch holes in this thing. I'm like, yeah. And we're going to have to exchange air, but we're going to have to pick the right product. And he's like, "Well, what does that entail?" And so I had to learn myself. So I'm super glad that you're joining us today. Tom is the technical trainer for Lennox. Tom, where are you joining us from?
London, Ontario, Canada.
Awesome.
And it's telling us that the weather is actually a little cool this year, unseasonably, where we're a little unseasonably hot. Tom's a little unseasonably cool. But even in Canada, you deal with these same scenarios, right? Exactly, Todd. There is a difference, and that's what we're here to talk about. Like, how do we solve these problems, and how do we pick the right products for those? So where do we begin?
100%, 100%. In Canada here, we've got, extreme cold winters, and we have air tightened up our hoses back in the 80s and the 90s to a point where, the problems that you were just, talking about there, moisture running down the windows like it was crying, were not uncommon, even back in the 1990s. And we had to come up with a better solution for air movement through the envelope than what we were doing in the past.
Okay. So that brings us into the topic of, now that we've got too tight of a home, we have to come up with a solution. And we are in the business of finding solutions, right? We are heating, ventilation, air conditioning, many times refrigeration. That V is one that gets overlooked a lot of times, not just ventilation from the interior perspective. We have to understand how to design ventilation from an exterior perspective as well.
Yeah, 100%, 100%. And the title here is a little bit deceiving. What's the difference? We'll get to that kind of at the end of the presentation, but we want to talk about the house ventilation, indoor air quality, because all of that is being affected by essentially the type of ventilation system we're going to include into our houses. Yeah, for sure.
Okay.
So as I started into this presentation, Clifton, at Lennox, we always like to talk about or start off with our core values here at Lennox: integrity, respect, and excellence. And I kind of thought, positive engagement and talent was two things that kind of fit with our audience here today. Kind of education and really talking about how we can improve things with the positive engagement. And so these are, as I said, our core values that we at Lennox try to accommodate and bring to our dealers, and then finally to our customers in every job, every application, every house visit we get to, for sure. So as part of the agenda here, these are some of the things that are part of the presentation: health and safety, indoor air quality, a little bit on high performance homes, different types of ventilation, some codes and standards across North America that have to be looked at and addressed and managed, and then some of the terminology that manufacturers use that is always confusing, whether it's AFUE or SRE or all the stuff that goes along with it. And then we'll finally kind of get to the end of the presentation as to what is the actual difference between these two products: heat recovery ventilators and enthalpy recovery ventilators. So that's kind of what we're going to be looking at here over the next little bit. Now, I always like to start off this presentation with this particular slide. 23,000 is the number of breaths we take in an average day from doing average things. And so, the big highlight of here is which one of these count. And the reality is that every single one of them counts, right, Clifton? Like, we need oxygen to live, and the cleaner that oxygen, the cleaner the air we breathe, hopefully the longer we live. And so this is kind of what we talk about when we're talking about HRVs, ERVs, or ventilation in general. Ventilation can take on all kinds of different names or results as to what we're trying to actually accomplish. But ventilation as a whole, and a real simple strategy, is the introduction of fresh air to our buildings to keep our occupants healthy and safe. That's our main goal with ventilation. We've got all kinds of different strategies for providing that fresh air, but the ultimate goal is getting that outdoor fresh air that you and I as a kids probably were kicked outside most of the summer that we got coming up here.
See, when it gets dark, kid.
Yeah, but today that's not the case, right? We don't spend as much time outside as what we did in past generations, and that indoor air quality is drastically affecting our health and safety and our quality of life. Talks about here that the Lung Association estimates that within our homes there are increasingly recognized threat to our respiratory health, and so that really starts to show up here. The Environmental Protection Agency lists indoor air quality as the fourth largest environmental threat to our country, which is kind of
Staggering.
unheard of, or hard to recognize that
Yeah.
the air that we breathe is actually having as much of an influence on to us as individuals as we just don't think about it. We take it for granted because we live in a nice neighborhood where we're not in the factories or those kind of areas, and so we think we've got a pretty good quality of life, but the air we breathe is certainly a big factor in that as we go forward.
We've got some
Maybe
really good heavy hitters joining us today in the audience. A Team Adam joining in. First time I've seen you in a while, my friend. This is right up your alley. He lives and breathes this, understanding the build environment. So, yeah, this is a really important conversation for a lot of people. And you made one statement that will help people understand, and it's the one term that gets so misunderstood. When we were talking about that HRV, that heat recovery ventilator, and then the ERV, and you said enthalpy
enthalpy,
recovery,
yeah,
right?
yeah,
Most people call that an energy recovery ventilator, which is incorrect. And I can't wait till we get into these definitions. We'll be able to help people
yeah,
understand the difference in
yeah,
those.
for sure. If we look at kind of the stats that go along with this, 90 million people in the U.S. suffer from allergy and asthmas. And I'd ask the group here, how many people in your house suffer from some type of breathing condition, or is there a family member that that suffers from breathing conditions, the quality of air? Elderly folks on oxygen on a regular basis for lots of reasons, but the air we breathe is certainly important. That's one out of three homes. 30% of the North American population have breathing problems. That's an astronomical number if we think about it in a big picture. And it all has to do, or most of it has to do with the air that enters into our lungs. Sometimes we do it to ourselves, right? We're not always the best if you're a smoker or some things like that, but certainly the air that we breathe on a regular basis, when you're indoors at work, when your kids are at the schools, at the dentist office, all that stuff is all affecting our quality of life. If I look at the fourth bullet point there, 90% of our time is spent indoors. And so if we look at that 23,000 breaths per day and we break that down to being 90% indoors, it's about 20,000 breaths that are of air inside a building envelope that is probably toxic in some shape or form. And we're going to look here at just another slide at some of the toxins that build up within our buildings. The air you breathe in your office space sometimes is better than the air you breathe in your home because of rules and regulations around building codes and things that go along with that. When you get into a large building, the building codes quite often will require a specific, indoor air quality with quite often all kinds of much improved sensors, CO sensors, humidity sensors, carbon sensors, all as a mechanism to keep that quality of the air and the workers that are making us money in a good condition and a good opportunity to come back every day.
Not very long ago, it's probably been 8 months, 9 months ago, when we were putting this mobile studio together, one of the manufacturers sent us a air quality measuring tool that measured a variety of different particulates, VOCs, formaldehydes. And my wife and I work from home. I work from home almost all the time. She works from home usually 2 or 3 days a week. And she said, so what is the quality of our air in this house? At that time it's like 5 years old. I'm like, it's probably not as good as you think it is. She's like, put that in my office. I really want to know. And we got a lot of poor measurements. She's like, where's all this formaldehyde come from? I'm like, are you really, you want the HVAC nerd to go there? And she's like, can you give me a briefing?
Yeah, yeah, the Coles notes that go along with it, right? Yeah, for sure. Yeah, we know that outdoor air is cleaner than indoors, and that's why we maybe didn't see this kind of 1/3 of the population with breathing problems, in the 50s and the 60s and
Right.
the 70s and 80s generation of my group, because we spent most of our times outdoors. Lots of the workforce was outdoors. Farmers. The factory work was there, but the doors were wide open and
Yeah.
that kind of stuff. And so we need to recognize that outdoor air is much cleaner than the air indoors that we actually breathe on a daily basis. And these are some of the things that we breathe on a regular basis. VOC, volatile organic compounds. The hairspray that we use here before I got into this, onto this webinar. So I look decent.
That's right.
That
Our
bathroom
makeup.
fills up with it. Carbon dioxide, biological contaminants such as mold and mildew. When we started to tighten up building envelopes, mold was rampant. And I've got a slide here a little bit later on that shows what mold can actually do to the integrity of a building. It's absolutely unbelievable if you've never seen it for yourself. You talked about formaldehyde. I look at these laminate floors that people are putting in
LVT
today.
everywhere.
It's used everywhere.
Every new home that I've seen.
It looks really nice. It's affordable. If you're going to do an improvement to your house, probably laminate flooring is one of the options that you are absolutely looking at. And that stuff can be just horrible if not monitored properly. There was I want to say 10 or 15 years ago, there was some stuff that was coming in from overseas that wasn't approved for the glues and the solvents that they were using, but it was being shipped in without any kind of looking at the parameters as to what the rules and regulations are. And there was millions and millions of board feet that were installed in people's homes that were, I hate to say it, but killing us on a slow, steady basis. And because it's slow and steady, you don't even recognize it's even happening, right? That's the problem with this kind of stuff is it's gradual. And so the off gassing of your Scotch guarded furniture that keeps the stains nice and keeps the stains off it. That stuff is all toxic to us as individuals, and we don't even know it's affecting our health until it's too late. I ask the question: how many people have animals within their house? I've got a big Newfoundland dog here. She's 135 pounds. I got a couple cats. The pet dander that's coming off those animals. But we love them, right? We love our animals sometimes more than our children, I think, some cases. But for those those pets that we love, they are also bringing in stuff on a daily basis. Every time we let them out to use the bathroom or whatever they might be doing, taking them for a walk, they're bringing stuff in. Viruses and bacteria. I don't know about you, Clifton, but I'm very susceptible to viruses and bacteria. For whatever reason, as soon as we get a change in season, I get a cold of some kind. When I go to your conference in Las Vegas, I can get off the plane, and a half an hour after I'm off the plane, I got a nosebleed. That dry Las Vegas air just kills me. I'm from the Toronto area in Canada. We're really high in moisture content, and so I like a nice moist condition. I talk to people about snowbirding. Are you going to snowbird in Arizona? Or are you going to snowbird in Florida? And I'm going to Florida. My mom, on the other hand, has to go to Arizona. She does not do well with a relative humidity above 40%. She gets a cough that just does not go away. And it was really kind of an interesting story. We didn't know what the cough was. It just kind of popped up there one day, and she had been to the doctors a bunch of times and just could not get rid of the cough that would come along with it. And then by chance, my sister lives, in the Toronto area, so it's a couple hour drive away. And my parents didn't want to stay with her when they went to visit, and so I put them up in a hotel because I do a lot of traveling, and I got some hotel points, so I could make that available to them. And when they came back from that trip, my dad said to me, I said, "How was your trip?" And my dad said, "Well, it's very interesting. Your mom didn't have a cough all weekend." And the light bulb went off in my head. I hadn't put two and two together, and I said, "What was the difference?" And he said, "Well, it was a really dry hotel room." And what it told me when that light bulb went off, it was environmental. It wasn't biological that this cough was occurring from. And so we started to monitor the relative humidity in the house more closely. Mm-hmm. And as soon as we can drop that relative humidity down below 40%, her cough goes away entirely.
That's intriguing.
And it was kind of interesting. I've been in this business for 25 years at that particular time, and I couldn't put the two and two together. That humidity, the relative humidity in that space could actually affect your quality of life and the conditions at which you live in. And so now that we monitor that relativity and we have devices that keep that RH down, she has a much better quality of life because of that.
Yeah, Les was just sharing, they're 103 degrees, but 13% relative humidity. I don't even know what 13% relative humidity is
Yeah, I don't
in the
know. I can't. That's
Midwest.
hard to imagine, right? It's hard
Yeah,
to
middle of
imagine.
winter, like dry is
Yeah,
upper 20s.
yeah. And I say it's hard to imagine, but now that I know a little bit about comfort conditions and what makes us comfortable or not comfortable, the house that I grew up in, I suspect probably had 11 or 12 or air changes per hour.
Mhm.
No insulation, single pane windows. When the wind
Nice
blew from the
enclosed
north, it
home.
came in the north wall and went right out the south wall, along
Hmm.
with all that heat and moisture. And that's really where my nosebleeds, condition started as a young child. And I think partially due to the environment that I grew up in the winters, having maybe a 11 or 12 or a 13% relative humidity all winter long is kind of evolved into the conditions, the problems that I have now with regards to dry
Right.
conditions. I'm
Right.
sure it has to do with the environment I grew up in.
Hmm.
Now, we talk about high performance homes, Clifton, but the reality is every home we're building is essentially a high performance home. We went from 11 and 12 air changes per hour in the homes of the 1960s down to 4.5, 5 air changes per hour in the 1970s, maybe down to 3 air changes per hour in the early 2000s. Today, when you get into LEED or Energy Star or our 2000 homes, we're down into maybe in some cases a half an air change per hour. I look at the Energy Star program; its maximum is 3.5 air changes per hour, with most coming in at around 2.5 air changes per hour. And for those folks who maybe don't understand what that term actually means, it's the amount of air volume in your house that either comes in or leaves in a 1 hour time frame. So, if you live in a house volume that is, 23,000 cubic feet of air, that air is leaving the building, which in turn has to re-enter the building 2 or 3 times in a 1 hour time frame. And when we talk about the economics of heating and cooling our buildings, that air change per hour rate has a substantial influence on the amount of heat or cooling generation that you require.
Absolutely. So we're going to have to
We can't
condition
we
that
can't
air.
yeah, we can't wrap our heads around how influential that is. When we do load calculations, it can be as much as 50% of the entire heat loss of your building can be due to air movement across that envelope. And so the savings that can happen when you reduce from 5 air changes down to 2 air changes per hour is phenomenal in dollars and cents. And when you talked about that story, that ICF home, insulated concrete form homes, those homes come in at quite often less than 1 air change per hour. And I knew as soon as you started telling me that story that his problem was I didn't get the fart part actually at the beginning, but I knew you were going to talk about the moisture running down his windows like a building was crying on the inside,
Yeah.
because that happens in every building that we've done in the last 20 or 25 years. We talk about high performance homes, but really all the homes that we're building today are really considered high performance. And the picture in the center of this slide here, this is the environment that we actually live in. We live in a garbage bag today. Okay. This is our house conditions. And when I'm talking to my students, I say, well, Ted's there, and I put a garbage bag around Ted's head. What happens to Ted in a real short period of time? And everybody knows what happens, right?
Yeah.
Ted passes out, and if the bag's around there long enough, unfortunately, Ted passes away. And we live in this environment. It's just a much bigger bag, but it's still that garbage bag that we're living in.
Man,
And when you get
what a
into
visual
spray
reference.
foam homes, these things are super super tight. And spray foam is easy, it's cost effective now, and it does a fantastic job as a thermal barrier for our buildings. It can reduce the heating and cooling demands of your building substantially. Yeah.
But at a cost.
At a cost for sure. Yeah. And the cost is our indoor air quality, like I say. There's all kinds of things here that are listed here with regards to high performance home and what the benefits go along with it. You talked about smell, that the odors linger around for a longer period of time, but they're also, generally speaking, a much more comfortable home. And again, when I'm talking to my students, we sell Lennox product, but the reality is we're in the comfort business.
Absolutely.
That's the business that I actually describe, and what makes up comfort. And there's lots of factors that make up comfort. It's not just temperature, it's sound, it's smell, it's humidity.
Absolutely. Oh, I hope I didn't lose you. Everybody in the chat, let me know if you're
I don't
still
know
getting
if that was
signal.
me.
Oh, there we go. Now you're back.
It came up as lost connection. Yeah, I don't know if that was my end or your end, but yeah, all these things. And when we talk about high performance homes, they become more durable, noise reduction, and hopefully they last longer for sure. That's some of the things we're hoping for. Now, when we get in these high performance homes, we have to start to consider kind of what goes on with this. And this picture on the left is what I was talking about, in a house that didn't control its moisture movement across that envelope properly. We know that hot air moves to a cold area, or heat moves from a hot area to a cold area, and hopefully we know that moisture moves from a high moisture content to a low moisture content. That's the physics of how those substances flow. But this is what can happen when we don't manage that moisture content very well. In this particular example here on the left, that cladding material, that covering material, was so rotted away you could actually pull it apart with your fingernails. It
That's
just
pretty
flaked
crazy.
off. And this was a home that had a very high moisture content, in the high 60% range, with poor vapor barrier performance installation. And so, we've got air barriers and vapor barriers. And if you're going to install a vapor barrier, you better do it right or don't do it at all, because these are some of the things that can start to happen. And it's that movement of that air. We can never stop the movement at 100%. It will always make a move. Around electrical outlets, pot lights and ceilings are just horrendous for the leaky areas of your building. If you've got any energy evaluators who are doing blower door tests, they know exactly what I'm talking about. We can see, through smoke tests, as to where that air is actually flowing when we depressurize the building and get that air to move. But along with that air movement is that moisture movement, and that's the diagram that we've got here is really what's going on. That moisture, as it starts to pass through the envelope, when it comes on in contact with a cold surface, such as that sheeting material or exterior cladding, the relative humidity goes up beyond the dew point condition, and then condensation forms. The water no longer, looks as acts as a vapor, or is in its vapor state, but changes to its condensed state, its liquid form, and that can start to build up. And these are some of the extremes that go along with the types of buildings we're building today, as a
Absolutely.
means of reducing our energy consumption.
One of the questions that came in from Zach was, are there alternatives to using foam ceiling, especially on the institutional level? We're primarily talking about the residential side in this conversation, but even in the commercial sector, we're seeing that the vapor barrier scenarios are really playing into the design criteria today. So yes, insulation is always a factor in the material that we're using, but those barriers, and especially in our vapor barriers, and the layers that we have in the exterior envelope are pretty critical. So we don't see as much of the spray-in foam in our institutional. We do see a lot of preformed foam panels, and then they're sealed into place, which is one of the primary constructions right now. But a whole nother section, if you want to learn more about that, I can get you some links later to some of the environmental management and construction from things like later if you want to learn more about the commercials.
Yeah, yeah. And unfortunately, the commercial side, the building code regulations can be a little bit lax on how we build that building envelope. because we're not occupying it, as much as maybe what we are in our homes, and the comfort expectations maybe aren't quite as great, because they want you to work, not necessarily sit in your comfy chair and watch the TV that lots of us do. Yeah. So why ventilation, right? Why do we do ventilation? Well, we talk about this sick building syndrome.
Yeah.
When you've got occupants in your building who are suffering from colds and flus and things, breathing problems, you really need to look at the environment that you're living in. Radon gas is a big factor today with regards to how it's affecting us. It's the number 2 cause of lung cancer next to smoking, right?
Really?
Radon gas, odorless, colorless, tasteless. And when they drop when they increase the acceptable, decrease the acceptable levels of radon in a building, we saw all kinds of areas open up with radon problems. For us here, we use a term called becquerels, and our limit for Canada is 200 becquerels. They want your building to be less than that. And it used to be thought it was kind of radon gas was only in mining areas and rock areas. But when they dropped that acceptable level to 200 becquerels, the map just blew up with regards to
That makes
the areas
total
where radon
total
gas was deemed to be present above acceptable levels.
Well, here in the Midwest, traditionally, we only did radon measurement, radon testing for the sale of a home if it had a basement. Well, the house that I have is on grade on slab, and we actually had a radon test being performed for the home. It's only 6 years old. That's the first time I'd ever heard of that, but it makes sense. We're actually lowering the acceptable levels, which is new environments.
Yeah,
Hmm,
yeah, for sure.
that's
Yeah.
interesting.
Um, the Hopefully we get some improved indoor air quality by the introduction of that fresh air. And we talk about we got that tight home, and then we got to go and cut a couple of 8-inch holes into it. But the benefit of actually what we're doing there is we're now controlling the amount of air that we're bringing in, and asking or causing to leave the building. And so when we can control the rate of airflow that happens with your building, we can still get the cost savings and the improved air quality. My building doesn't need ventilation. Me as an occupant needs the ventilation. And so, if I go away from work, I don't need 5.5 air changes per hour because there's nobody in the house occupying that space. It's when I come home and spend 8 hours, or hopefully 8 hours or 6 hours worth of night sleeping. That's when we want that amount of fresh air,
Quality air.
that fresh air being brought in, because we're the ones that are actually breathing it. Now, if you've got pets and things of that nature, that might change your opinion as to whether your house needs to breathe in the middle of the daytime when we're at work. But ventilation is about satisfying the occupants, not the actual building. Under some circumstances, we can influence moisture, or have some control over moisture influence on the building. It through ventilation. It only happens in some very specific scenarios where we can actually influence the relative humidity of a space. And for us up here in Canada, and again, it has to do with that relative humidity between temperatures. Temperature changes, so does relative humidity. And so when we bring in cold outdoor air in the middle of January and we warm it up, it actually has a drying effect onto our building. So I can get some moisture reduction benefits in a climate like Canada, but I don't get those same moisture drying effects if I'm in Florida. Actually, the opposite
Exactly.
is happening, and so that becomes another factor in the choice of whether we're going to choose an HRV or
Which
an
system?
ERV.
Okay.
Odor removals, longevity of building materials. Like you see that house that I was looking at, that picture of that rotted out wall, that was only 5 years old. That house was 5 years old and it already was that bad.
That's crazy.
Condensation control, reduce allergens. High occupant numbers can really also affect the amount of ventilation required. And that's actually how we deem how much fresh air actually needs to be delivered to houses, based on how the building's being used, the number of occupants that are going to occupy that space, and so forth and so on. All of these things are affected and can be improved. We'll talk about mostly about being improved when we add ventilation to our buildings. And again, ventilation takes on when I think about ventilation, if I asked a general homeowner, what is ventilation? They're going to say, well, it's my bathroom fan.
Right.
That's the device that's providing the ventilation. And when I say a bathroom fan, well, I know I'm taking that air out of the room. What we forget is when I take 100 CFM out of a building, 100 CFM has to come into the building. And it's really the 100 CFM that comes in that is more important than the 100 CFM that is going when I turn on a bathroom fan.
Completely.
So that moves us into the different types of ventilation systems available to us. We got natural ventilation. That's what we relied on in my dad's generation, my generation. He opened up the windows. I grew up in the 1970s, and air conditioning was a luxury. I don't know about your building code where you are, Clifton, but in the Canadian building code, air conditioning is not mandatory. It's considered a luxury item.
It's an option.
And yet every home in southwestern Ontario where I live, because of the high relative humidity in summertime, just has an air conditioning. It's become standard practice. My kids don't know any environment that doesn't have air conditioning. Even the schools we go to today have air conditioning. What wasn't the case when I was a kid. We opened up the windows. When it got hot, you open up the windows, and in those summer evenings because our house had no insulation and it was 85 degrees in the house, you went outside, right? Again, it's about being outside. Crawl space ventilation, dealing with moisture problems. When you have buildings with crawl space, typically the problem is moisture generation. You don't have any air movement, and so that moisture starts to build up because of the moisture that's being introduced through the ground that it's connected to. Attic ventilation we sometimes see in areas where you're trying to reduce the heat that's in an attic, say in California or Arizona.
Yeah, we do here.
Sometimes, however, that can cause more problems than what it actually solves. We think we're solving a problem, that we're removing that hot 120 degree air of the attic, but now it creates a negative pressure influence, and that the greater that negative pressure influence, the more that air moves across that building envelope. So we think we're fixing one problem, and you're actually creating an entirely new problem that may or may not even be recognizable.
Great perspective.
Mechanical ventilation is really what the building code looks at. And we really have three strategies. We've got exhaust-only ventilation, which is the bathroom fans that I talked about, supply ventilation in kind of some of your southern climate zones, and then balanced ventilation, which is today's standard for providing fresh air to our buildings, and that's typically comes in two forms, as a ERV or an HRV. It doesn't have to be an HRV or an ERV. A balanced ventilation system could be an exhaust fan that moves 100 CFM out of the house on the north side of the building, and a supply fan that brings in 100 CFM of air on the south side of the building. That would be still considered a balanced ventilation system. It just doesn't have any energy or heat recovery that goes along with it.
Yeah, I've actually seen some residential exhaust hoods that are using that philosophy, that are tied into incoming air fans, just like we would do in a commercial application. So the exhausting fan is actually intaking air in the same process. So the exhaust for a residential kitchen actually is a two-pipe system, one for exhausting and one for fresh air.
And that was pretty standard. And again, here in Canada, we're only, for the most part, only using high efficiency gas fossil fuel equipment today.
Sure.
I know down in some of the states where you are, they're still using natural draft venting systems for their fossil fuel appliances. And those appliances can be really affected by the imbalance of pressure that's created in either an exhaust only or a supply only system, where a balanced system, like it suggests, it's balanced. And so it's less, there's less influence on, say, or the less likelihood that backdrafting can happen on wood fireplaces or natural draft chimneys or B-vented systems in that of the combustion strategies that we're using today to get rid of those products of combustion.
A lot of people don't realize, like even with the wood fireplaces, like I just out there on the barn dominium at the farm, I installed an EPA certified wood fireplace. And part of that certification is that it actually is bringing its own combustion air. It is a two-pipe wood fireplace. 100% of its combustion air is coming from outside, so that you don't have those changes on your envelope. So we're starting to see that in a variety of different applications.
Yeah, absolutely. I used to have one when I lived out in the Nova Scotia, in the eastern part of Canada. But every time you open up that glass door, you're now taking some of the air that's inside your house. And we had a fireplace where I could take that glass door off and put a mesh screen onto it so I could hear the snap, crackle, and pop of that wood. And when you do that, then that fresh air actually doesn't
Doesn't
work
make
as
its way.
effectively as what it did when that stove sealed up nice and tight.
Mhm.
Now, this exhaust ventilation is the strategy we've been using for the last 5 decades, right? Like since the 1960s. We installed a bathroom fan, an exhaust device, could be a range hood, could be a bathroom fan, as a mechanism to remove the moisture, say when you were having a shower, where that moisture buildup was intense. We've all had a hot shower on a January day, and you've been outside working or cutting wood or whatever it might be, and you just want to get warmed up, and so you crank that shower up, and your bathroom's full of steam. Some people will open up the window. That's a good option to kind of get rid of that steam, and other people will use a bathroom fan as a mechanism for removing that. Again, what I talked about, the bathroom fan is removing the air from within the building at a rate at which it was designed for, 50 CFM, 90 CFM, maybe 110 CFM. They come in all kinds of different sizes. But what it's really doing is it's creating a negative pressure imbalance within the building. And because of that negative pressure imbalance, Mother Nature always wants to come back to a balance. So what goes out must come in. Now, the looser or the tighter your house will influence the amount of air movement that can occur across your building, and the size and the capability of your fan will influence how much air can also move, right?
Yeah.
And unfortunately, today's bathroom fans don't have a great amount of power. Their external static pressure capabilities generally are pretty low in nature. They're certainly not like we might see with a furnace with 0.7 or 0.8 or even 1.0 inches of external static pressure. These are half
Shaded pole, low
or a
efficiency.
0.1 or a 0.2, right? They just don't have the ability to overcome the resistance that we've created in a what I'll call as a high performance home, which are really every home that's being built today. But again, what I want us to kind of understand here is it's all about the bringing in of the fresh air. This was just a device that created a negative pressure imbalance that caused that fresh air to enter into our buildings. Really popular in the northern parts of the US and into Canada. We think about winter months being the dominant season when you've got things sealed up. That's when your windows are closed and your heating system's on. And it's that introduction of cold outdoor air and then warming it up, which has a drying effect onto your building. If I try to use the next strategy here, which is a supply only system in Canada, this would positively pressurize my house. And if I tried to use this strategy in Canada, what it would actually do is it would push that moisture into the building envelope. And then that slide that I had earlier, where you start to see condensation forming, that's what it would do on a regular basis. So in cold climates, we don't use a supply only strategy. We generally look to an exhaust only strategy because of those winter conditions.
Makes sense.
When you get down into the southern parts of the U.S., however, they might choose to do the supply only because now we're trying to keep that moisture out of the building. I think about the summertime in Florida where it's 60 or 65% relative humidity. By pressurizing that building, I'm pushing the air out of it as opposed to letting it come through the building envelope. And so again, we're going from a conditioned to cold condition, house in Florida, and we're pushing that to an outdoor warm exterior. So as that air moves through the building envelope, it actually has a drying effect as opposed to a moisture generation effect that we would see here
Sure.
in Canada. But both of these strategies, as it says here, are 0% efficient. There's no energy or heat recovery that happens, unlike what we look at with an HRV or an ERV. And these devices have a heat exchanger essentially, and a heat exchanger is just a device that has the ability to transfer heat from one side of a plate to another side of a plate. And that's where the energy efficiency really comes in. Not only do we get to control the amount of air that we bring in or move out of our building, but we also get some energy recovery. And so the BTUs that would be required to, say, heat the air up from 32 degrees Fahrenheit up to 72 degrees Fahrenheit to keep me in a warm environment, I might be able to save 70 or 80% of the heat energy that my furnace no longer has to deal with by simply transferring the heat from the warm air stream into the cold air stream. And again, I'll use Canada as kind of the example here in a winter environment. If I've got 32-degree air entering into my building, I have to warm it up to 72 degrees. Let's say that takes, doesn't matter. Let's say it's, keep the number simple. It's 3,000 BTUs.
Yep.
Okay. And I can save 2/3 of that through the hot air that I'm pushing out of the building at the same time. So I bring in this 32-degree air, and at the same time I exhaust 72-degree air, and I get 60% transfer of heat energy from across the two air streams. I took my 3,000 BTU load that the furnace would have had to deal with, and I reduced that down to 1,000 BTUs of load. And that didn't cost me a dime, Clifton. That transfer of energy is 100% free. I have to ignore the concept of the motors that are moving that air, because that's going to happen whether I have a bathroom fan with a motor or a supply fan in the motor. We talked about a balance system could be as simple as an exhaust fan on one side of the building and a supply fan on the other. That motor energy is still happening, whether I move that air across the heat exchanger or not. So in that picture, I want us to ignore the cost of energy that we use to run the motors, because that's going to happen
in any
whether
scenario.
there's a heat exchanger or not. And the heat exchanger is a simple device that allows that heat transfer to take place. And if we look at, say, an HRV, most HRVs are made of an aluminum core. And aluminum is a very conductive metal that allows that heat transfer to pass very well from one side of the plate to the other side of the plate. The other thing we want to kind of talk about with these systems is that the airflows, the exhaust side airflow and the supply side airflow are 100%, well, 99% independent of one another.
Mm-hmm.
So what's happening on the exhaust side, Clifton, has no influence on what happens on the supply side of the system. The plates themselves, or the air streams themselves, are separated by those heat exchanger plates. There is a little bit of cross contamination,
just within the shell,
pressure and balance,
yeah,
but it's within the box. But that's typically less than 1% or maybe 1% of the overall airflow. So that's why I say it's not quite 100%
sure
airtight, but they're darn close. The manufacturers are really working hard to even reduce that. Now they're building pre-manufactured plastic boxes as opposed to metal boxes that we see, which they can now control the cross leakage that happens between those airstreams even better today than what we saw in the past. And that's kind of where the HRV, ERV manufacturers are working today. How do they improve the transfer capabilities of their cores? How do they improve the cross-contamination that happens between those two airstreams? And then what kind of motor usage are they using? Today we're into ECM motors that are more efficient and use less electricity, because we want these things to run, for the most part, 24 hours a day. And I always get the question, well, what does that cost me in dollars and cents? And my answer is, well, what does it cost you in your health? Like, what's your health worth? If that costs me $15 a month to run that system, and you can live 5 more years because you've got better indoor air quality, was it worth the $15 a month?
Yeah, that's cheap insurance.
We have to put it into a context that people understand, as opposed to, well, that's just cost me a bunch of dollars. Or my bathroom fan, I have to run it for 20 minutes and I'm having to shower. But the other 40 minutes, you're living in an environment that doesn't have a whole lot of air changes, and that indoor air quality is being affected because of that.
Intriguing.
Yeah.
So by design, what are we seeing as differences between the HRV and the ERV?
The core material itself is really the main difference. And as I said, when we get into it, I'm not sure what our time management is here, but when we get to the end of this here, it's really about the transfer capability of the cores themselves. And I'm going to hold off on that, Clifton, for a little bit of suspense for the folks that maybe don't really know what the difference is.
Okay.
But yeah, it's important that we understand that, again, The energy transfer that happens in these devices is essentially 100% free. And what happens on the exhaust side has no influence or bearing as to what happens on the supply side, which is really nice. It doesn't mean that I have to have, I think about furnaces on the intake and the exhaust of a high efficiency furnace. Typically, they have to be on the same side of the building for pressure so that you don't trip your pressure switch and things of that nature.
Sure.
We don't have that same problem with this. If you want to put the exhaust hood on the north side of the building and the supply hood on the west side of the building, be my guest. What happens to one doesn't influence what happens to the other, which can be good for a bunch of different reasons.
Yeah, especially for installation.
Yeah, for sure. And when we're talking about condos and townhomes where exterior wall surface areas is
Limited.
hard to come up with sometimes. We got codes and standards that we have to adhere to with regards to ventilation. ASHRAE, the American Society for Heating, Refrigeration, Air Conditioning Engineers, is a U.S. Group.
Yep.
They write all kinds of standards. They do testing criteria. Hopefully, everybody on the call has some understanding of ASHRAE. If you don't, go look them up. They're a great grassroots association worldwide. They're all over the world. They're the leaders in testing for different criteria, and they're just a really good organization. They make up two standards. One, essentially for commercial buildings, which is ASHRAE 62.1, and then they make one for residential buildings, ASHRAE 62.2. And these two standards set the rules and regulations around how much fresh air you actually have to bring in. And I'll talk about how we do about that in just a second. In Canada, we have this CSA standard, F326, and it's similar to what ASHRAE is, but because we're different, we've got to be slightly different. We're the same, but different, if that makes sense. Like the Canadians of the US, we're the same, but we're just different, right?
Exactly.
Essentially, we're all the same. And so the Canadian standard isn't a whole lot different than what the US standards are.
Yep.
I also want to just point out here, HVI, the Home Ventilating Institute. This is an organization that was essentially created by the manufacturers of ventilation equipment. And they came up with a strategy that made all testing across equipment compatible so that we could compare apples to apples. They come up with what needed to be tested, how it needed to be tested, what temperatures it needed to be tested at. And today they're all across North America. They do testing criteria and set codes and standards around range hoods and bathroom fans and attic fans, and again, HRVs and ERVs. And I'm pretty sure it's the same for you folks in the US. It might be different state to state, but in Canada, in order to use an acceptable ventilation appliance, whether that's a bathroom fan or a range hood fan or an HRV or an ERV, it has to be HVI certified. So all the manufacturers do all this testing to send it through to the HVI. They do testing on it, and then they do periodic testing to make sure that the manufacturers aren't fibbing us with their specifications.
Yeah.
And it just keeps everybody on an even playing field. But what's nice about this is they have an entire database of every certified ventilation piece of equipment with regards to what its performance capabilities are, what its CFM values are with regards to blower capabilities, how many CFM do we get for this external static pressure? What's the core transfer capability of it? And so they list all that information in one central location. So it's great for designers or engineers as a place to go to pick equipment that's going to meet their needs and their expectations.
Yeah,
it's really phenomenal association. Equipment sizing is kind of what we got here now. And as I said, the sizing is based on the standards. Now, this is 62.1. It's more for commercial applications, but essentially it takes into consideration four things. It takes consideration as to how the building is going to be used. Is it a library? Is it a gymnasium? Is it an office space? And it's going to assign a ventilation rate for the type of building that is being occupied. And then it's going to assign a ventilation rate per person that is going to be using that space. So somebody in an office, say, is probably going to require a lower ventilation rate per person than somebody who's in a gymnasium who's working out, who's using a lot of oxygen, right? So it sets the types of buildings that the ventilation has to be provided to, the rate at which the occupants are essentially going to consume that fresh air, and then it looks at the size of the building, and again, um, how that building is being determined. So it takes those four pieces of information, and with that we can calculate what the ventilation rate is. And the formulas here with the acronyms that go along with it. I'm not going to get into all the details in the hour we've got here, but that kind of is a brief explanation of how they do it commercially. Residentially in ASHRAE, they do it slightly different. They still consider the area, and they essentially assign 0.03 air changes per hour per square foot of floor area. So we look at the size of the building, and it's for every level that be occupied space. It's not the area of the footprint, but the area of all levels in the building added together. And then we assign 7.5 CFM per one individual that'll occupy that space, plus one, with the assumption that there's going to be two people that occupy the main bedroom or the master bedroom that we would think of. And so it's the number of people plus one based on the number of bedrooms, and that essentially what determines the amount of fresh air that our building would require. So, if I looked at this here, if we had a 2,000 square foot house, so on 1501 to 2000, and it's 3 bedrooms, we need 90 CFM of fresh air being delivered to that space. I can do that with a single 90 CFM bathroom fan. I could do it with 245 CFM bathroom fans, or a combination of a bathroom fan and a range hood. I could do a combination of a 45 CFM HRV and a 45 CFM bathroom. They don't have any real requirements as to how or what strategy we use. This is just the minimum number that we have to deliver, and this is the minimum. There essentially is no maximum. You can never have too much fresh air.
Right.
If we're talking health and safety, but there is a cost that goes along with over ventilating a building, and that's kind of what has happened here in Canada. In Canada, we use CSA F326, and they made it even a little bit simpler. They essentially assign fresh air delivery rates for types of rooms that we have in our houses. Sure. And so we got this list of the general types of rooms that you would have in a house, and we simply assign a CFM value for each room, add it up, and that's the total. Now, this is an older version of the CSA standard. They've slightly tweaked it, and they've gone more to the ASHRAE standard, where it's 7.5 air changes per hour. And they did that because this was actually it was a great strategy, nice and easy for contractors and designers to quickly do the math. But we found that we were actually over ventilating homes. And so, not that that was a bad thing, but there's good and bad to everything we do, right, Clifton? And so when you overventilate a home, the equipment was bigger, so it had more capital costs. The ductwork was bigger, and so forth and so on. And actually, in wintertime, we started to find, with the use of HRV specifically, that we were actually over drying out the buildings. We were causing not a comfortable relative humidity, but an uncomfortable relative humidity. My windows weren't sweating at all. But I had RHs that were down in the 30% range, which is just typically lower than what most people are comfortable with. And so they've gone to as I say, the other strategy, number of bedrooms, and that seems to be a little bit more appropriate. So that CSA standard has just been reaffirmed here in 2025, and when I talk about CSA, this is just a nice, simple way that people understand, and I can still use this strategy. I don't have to go to the newer versions. The building code still references this older version, so I can still use it, and it's just still nice and simple for people to understand. It doesn't have to be a complicated strategy for sizing a piece of equipment, and because I'm in Canada, and I get lots of calls from the US folks that ask me about HRVs, ERVs, and the number one question is, how big does it need to be? That's always the number. They understand the concepts, but they don't generally, contractors don't have a real good understanding as to how we actually size that. And it's one of those three strategies is what we use. Now, when we talk about the use of an ERV or an HRV, it's going to be influenced by the 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 moisture content of the outdoor air.
Yeah.
So am I in a dry area or am I in a moist area? Okay. And so this is kind of a nice simple map that kind of breaks up the US into a dry zone area and to a moisture zone area. Because the moisture, exterior moisture will play a factor as to whether I'm going to use an HRV or an ERV. And I'm maybe already kind of giving away where I'm going to end up here at the end of this presentation as to what's the actual difference. We also look at the temperature zones that go along with this. Okay. And so where I'm here in the gray, I'm not quite in the gray, I'm in the purple here where I am in southwestern Ontario. Actually, I'm in the green where I am, but this looks at climate temperatures, and that will also play a factor as to whether I'm going to use an HRV or ERV. When they first came out, it was generally assumed that an HRV would be used in a cold climate and an ERV would be used in a warm climate. That is starting to change pretty significantly, actually, Clifton. And we're starting to see ERVs as a more viable option, even in colder climates today, because of the two reasons. One, we were oversizing our ventilation systems to begin with, and we were actually reducing the relative humidity in homes to a point that was becoming uncomfortable.
Okay.
Where ERVs actually do a better job of maintaining a relative humidity as opposed to reducing a relative humidity in a cold climate zone.
Okay.
So
That makes sense.
again, I'm kind of giving away here if you're picking up on some of the cues as to what the actual differences are. But using an ERV in even my climate zone allows me to get higher ventilation rates without reducing my relative humidity to a point that is lower than what is generally considered to be comfortable. And I don't have it as part of the slide, but the industry suggests that 30 to 55% is an optimum range for relative humidity. That's what the industry says.
Mhm.
And the industry has kind of came up with that range mostly because when you're in that 30 to 55% relative humidity range, things don't grow very well. Mold doesn't thrive very well. Viruses, bacteria, they don't have the conditions that make them thrive. When you get to the extreme moisture or to the extreme dry, that's when these things start to really start to take off. And so, I ask my students, what is your optimum relative humidity? And I'd be curious, Clifton, to know the people on the call, what if I asked you, what is your optimum temperature?
Good one.
I know everybody in this room, in this call, has a number. As soon as I say, what's your optimum temperature? It's 68 degrees, it's 70 degrees. It's the temperature set in your car when you look at your digital heating device in your car today, or your digital thermostat. But if I asked, what is your specific optimum relative humidity for you, I suspect less than 50% of the calls actually know. And if you know, I'm going to tell you to put it up, let Clifton know what your optimum number is.
Yeah.
As I said, I need a snowbird down in Florida. Mine is in the high 40 range. My mom's is in the mid.
Man, that's right. At what relative humidity?
Relative humidity, we could spend a whole hour on what is relative humidity. So I won't get into there, but because he's 13%. I just got that part. Yeah. What is relative humidity? Yeah, for sure. And so as comfort advisors, as individuals that are selling comfort, it is an important factor on our customers' comfort considerations is what is their optimum number. And the only way we start to know that number, Clifton, is by monitoring it, right? We know what our optimum temperature is because it's what you set in your car. It's what you have your thermostat set in your house. But we don't have any, in the past, we haven't had any devices that told us what the relative humidity of our houses are.
Mm-hmm.
Now, lots of controls today now start to monitor what relative humidity is. It's quite often not on
based on humidity
front of the screen,
Mm-hmm.
but if we can make it so that people start to recognize their comfort as to what the relative humidity is, we can start to influence how we deliver comfort to that house. We know that in summertime, if you got your air conditioning running, controlling the relative humidity can make a huge difference on what your temperature needs to be. But we just kind of forget about the relative humidity. We know we have to control it, but we don't really know what we need to control it to, or what it should be for each specific individual.
Absolutely.
Yeah, for sure. Um, this is kind of just a summary here of what we talked about.
Okay.
It's a good suggestion for people if you took a snapshot of this or whatever. A cold and dry climate is generally considered to be an HRV, prime condition for an HRV. If we're into a hot and humid area, ERVs tend to be a more of the viable option. A moderate and mild, okay, that's kind of where I am here in southwestern Ontario.
Mhm.
Again, this 15 years ago was HRV territory across the board,
No
but
kidding.
ERVs are really starting to make much more sense for us. And if you're into a cold and humid environment, it could be either one. There's some other factors that start to influence our choice, and this is the list here. The air tightness of the house is going to play a factor in that. Your occupant preference, or occupant numbers. How much moisture is your household generating? I've got a 2,000 square foot bungalow with a finished basement, 4,000 square feet of living area. That there's me and my wife. There's two people live in this house. It's a 5-bedroom house. We don't create a whole lot of moisture. But if the kids come back from college and we cram 6 or 7 individuals into this house, there's a whole lot more moisture being produced. And so the exact same house, when there's just me and my wife, an ERV really starts to make a whole lot of sense. If the kids come back from college and we've got 7 people in the house that are doing washing, showering, cooking meals, breathing,
Yeah.
my moisture concentration goes way up, and now maybe an ERV doesn't make a whole lot of sense. So we can't just look at wet and dry outdoor conditions and cold and warm locations. We also have to look at how is the building itself being used. In Canada here, our First Nations groups tend to be up in the northern part of the country. Um, and unfortunately for those folks, they live in really small houses that are jam full of a whole bunch of people.
Yeah.
Okay. And so you've got, small homes that are 1,400 square foot, slab on grade maybe, and there's 5 or 6 people occupying that house. And they're producing so much moisture in that small environment. You start to see the problems that we looked at on that picture of that sheathing material rotting away. That's where that picture came from. Was a northern First Nations community that didn't control the relative humidity. They were in an extreme cold climate, and that heat and moisture just wicked its way to the outdoors, and that's what happened 5 years later.
Wow.
Poor installation of the moisture barriers and the general construction of the overall building. So unfortunately, those folks, pay a price for the climate zone that they live in. And then, what kind of a system do you have? HVAC system? Are you heating or cooling your house with mini splits where you don't have a duct system? Fresh air is great, but it has to also go to the areas where people need it the
Yeah, where it's being
most. And
served.
we need it the most in our bedrooms. We sleep in our bedrooms 5 to 8, maybe some people 10 hours a day. If I dump all that fresh air into the kitchen and we spend 8 hours of our day in the bedrooms, it doesn't do us any good. So we quite often reference the term, it must be distributed to be effective. And so, do you have a air distribution system already in place that allows us to do what we call a simplified ducting installation, or do you have hydronic, heating, or electric baseboard heating, or a mini split system that doesn't have any ductwork? That will dictate how that distribution strategy is required, based on the HVAC equipment you have in your building. So it's the climate stuff that we talked about, but it's also this other things. And the biggest one there really is occupant. They call it preference, but it's really occupancy numbers. How are you using your particular structure?
Okay.
Now, some of the terminology that manufacturers use, and I, I don't have time to get into all this, but it's off the chart. There is lists of all this stuff. Apparent sensible effectiveness, apparent total recovery efficiency. They all take on these different terms. These are just some of the ones that are available to us. But there's a couple I want to focus on in this presentation. And the first one here is the apparent sensible effectiveness, or it's ASE. This is the description of the heat exchanger itself, its ability to transfer heat from one airstream to the other. Okay. So this apparent sensible effectiveness number is a direct result of how good or how poor your heat exchanger itself is made. If I look at an HRV, we've got HRVs where the cores are made of aluminum, and I've got other ones that are made of plastic, some type of plastic. The aluminum core typically does a better job of transferring the heat than a plastic core. So an aluminum core will have a higher ASE than a plastic core. Now that's changing through technology, but as a simple kind of understanding as to what that number represents, that's what that one is. And we use this to determine what the delivered air temperature of the air is when it comes out of the grill, right? Remember, it started off at 32 degrees Fahrenheit. We warmed it up. How much did we warm it up? What's the temperature coming out the grill? Because that's what's going to be really important to most individuals who are occupying that space. If that air enters out of that supply grill at a temperature that's too cold, people are just going to shut it off, or they're going to stuff it full of insulation. And so we have to be able to, through a math calculation, calculate or determine what that delivered air temperature is, so that people aren't affected to a point where they want to shut off. Imagine sitting in your lazy boy chair and you got a fresh air grill that's blowing 65-degree air across you. You're quickly going to shut that off or cover it up. You're not going to be willing to use it. So we have to manage that delivered air temperature really well, and this is how we determine that, through the apparent sensible effectiveness.
Yes, our sensible heat transfer.
The other one, go ahead, Clifton.
That's just our sensible heat transfer. What percentage of our sensible heat are we transferring through the heat exchanger?
Yeah, you got it. The other one here is the SRE, the sensible recovery efficiency. Okay. And this is typically used by building or energy codes as minimum standards. And so it dictates essentially the electrical consumption as compared to the heat transfer. So it's energy as a whole, right? And energy takes on all kinds of different forms, as hopefully as we all know. So this considers electrical energy, heat transfer energy, and considers all that and gives us a number so that we can essentially evaluate how beneficial in dollars and cents that will be to our building. Okay.
Awesome.
It takes into all this stuff listed here: the defrost time, the motor wattage, the cross leakage of the core. It's typically measured at two conditions: 32 degrees Fahrenheit and minus 13 degrees Fahrenheit, for different climate zones at which you might be installing this particular piece of equipment. And it's generally looked at a CFM of 60 CFM. If I change the temperature, if I exchange the delivery rate of the air, the amount of CFM, it changes the sensible recovery efficiency. But it kind of goes along with that.
Very cool. Well, Tom, there's a lot more we can dive into. I see a part 2 coming up for us, where we'll dive even deeper into this. I appreciate everybody hanging in with us. It's an intriguing topic that really needs to be understood better. And Tom, you are the man for filling us in.
I don't want to, if I can, because I ran out of time here, Clifton. I thought I had 10 more minutes, but I've run out of time here. So what is the difference? And the difference is an ERV has the ability to transfer both heat and moisture across heat exchanger, and an HRV can only do heat. So if I put it in simple terms or technical terms, an HRV transfers sensible heat only. An ERV will transfer both sensible heat and latent heat. And so it allows me to manage my moisture removal much more specific in an ERV than I do in an HRV. And maybe a part 2, because
absolutely.
I ran out of time to get to the slide that kind of helps describe that.
We can jump over there if you have one more that we want to look at. unless you want to do it
Yeah,
as a
if you
part
don't
two.
mind, if I got a couple minutes, Clifton,
Yeah.
and I'll just jump to it here. Um, just some controls that go along with it. Balancing these systems is really critical in order for them to function properly. And if I just talk about the what the difference is here, as I said, the moisture transfer that happens. So this is
Oh
an
yeah, it's a lot
HRV.
of good
If I
stuff.
look at the moisture molecules in these two drawings here,
Okay.
so if I look at the core in winter, I don't know if you can see my mouse moving around here, but if I look at the core in winter, if I've got indoor air moving out, that's where it's at its highest moisture content. I got 4 grains of moisture in this airstream. I don't know if can you circle that, Clifton, or do you have a pen or
Oh,
anything
I
that can do
don't
that?
have one on this one. I sure don't.
Anyways, we've got 4 grains of moisture in the air that's leaving the building. As it
Sure.
transfers through the core, all 4 grains of moisture leave the building. Okay. Which is a good thing. It has the ability to dry out my building. But in the summertime, the opposite is occurring. If I try and use an HRV in Florida, I bring those 4 grains of moisture and dump them right into the house that the air conditioning system has to deal with. If I go to the next slide here with an ERV, what we see here on the picture on the left in winter is, in this example, I've got 5 grains of moisture that are leaving the house. That's the water droplets.
Mm-hmm.
2 of those grains will move to the outdoors, but 3 of those grains will stay indoors. And that's where we get the ability to not entirely dry that air that's being left, but
Right.
being able to manage it better.
Return it.
So it doesn't dry it out. It manages it more appropriately. And so I can have higher ventilation rates without reducing the amount of moisture that's
Moisture
in
in
the
the
house.
air.
And in the summertime, they're really benefit. Again, if I'm Florida and I've got 5 grains of moisture that are coming in from that 80% relative humidity, 3 of those grains stay outdoors and only 2 grains move indoors, and that's where they're really beneficial in the summertime. And then just to finish this up, Clifton, here, this is just kind of a snapshot of kind of the comparison between the two as to where they might be used, where they kind of are best performed, so forth and so on. But otherwise, that was the end, Clifton.
No,
So
that's great stuff, Tom.
let's
Like I said,
wrap it up
everyone's
here
enjoying
too.
this. I mean, everyone out there is going, "Yeah, we need a part two to this."
Yeah,
I love how passionate you are on understanding this because it was such a misperceived difference between the two. And as HVAC professionals, ventilation professionals, we need to understand what the difference is between the two because they function completely different in certain environments, and we have
that's
to
right.
know how they function.
Yeah, yeah, and it's not a one size fits all. You really have to look at your location, how the building's being used, what are the expectations of the individual that's actually using it, and when we have a better picture of what all that looks like, we can make much better informed choices that'll keep our customers in a much more comfortable environment, happy. And they can save some dollars and cents that goes along with it. And when we can do all of that, we look like masters, don't we?
Yeah, absolutely. And that's the goal, right? We are the
That's the goal.
professionals and we should look
That's right.
professional.
Yeah, yeah. I tell people, give individuals all the right, the good and the bad information. Let them
Let
make
them
the
make the
choice
choice.
that best fits them. And the better I know my own content, the better I can actually manipulate those individuals into making the good choice that I know is right for them. But it's not my job to tell you what you need. It's my job to steer you down the path that allows you to make the best choice possible for you and your family.
I love hanging out with you. I encourage
Yeah, I
everyone that's enjoying this conversation, come spend some time with Tom. Tom always joins us at the National HVACR Education Conference. This is just one of the classes that he has done for us. And I'm sure you would enjoy just picking his brain and diving deeper. So I encourage you to reach out, get to know Tom better. Hello. I know it's a lot of information. That's why you get to come back and go through it. And we'll maybe we'll dive a little bit deeper, and maybe we'll Professor Silberstein, I noticed was up there
That's
eating
what I
those
was thinking.
Carolina
Yeah,
Reapers. So
yeah.
maybe he'll come back
Take
and
take his psychometric class at the conference, and you'll be astonished. He blows me away. I've seen it 3 times, and he gets me something new every single time I've seen it.
I agree. Well, thank you so much for joining us today. It's fantastic conversation. So glad everyone took the time to hang out with us to educate yourself on ERVs and HRVs. Reach out. Don't be afraid to contact Tom and learn more about uh, just HVAC solutions. You got to remember, Tom is here teaching you about HVAC fundamentals and principles. We haven't even dove into the equipment from the Lennox Learning Solutions, so there's a lot more to dive into there. I encourage you all to check out Lennox Learning Solutions, and we will see you all again next week on Did You Know, the ESCO HVAC Show. Bye, everybody.
Thanks, Clifton.
Thank you.